All right, hello everyone. Welcome back to the HoTT seminar. This week we have Fredrik Nordvall Forsberg from the University of Strathclyde, and he'll talk about different notions of ordinals and homotopy type theory.
Right. Thank you very much for the introduction and for the invitation to speak. I think this is a great seminar. So I'm going to talk about some work in homotopy type theory today, not so much about the foundations of homotopy type theory. And this is joint work with Nikolai and Changyi from Nottingham and Munich. So this is about ordinals in type theory. And I guess most of us at least have some intuitive notion of what an ordinal is, that it's something you use for counting or ordering things. It's almost in the name, right? So you start counting 0, 1, 2, etc. And then normally you never stop, but with ordinals you can reach infinite things. So you reach omega after counting all the finite things, and then you start counting omega plus 1, omega plus 2, etc. until you reach omega plus omega, and then you keep counting omega plus 1. So that's what we usually call omega times 2 plus 1, etc. And then omega times 3, and we can take the limit of this and we get omega times omega, and then we could always keep going, right? And we can reach omega to the power of omega, and then we can iterate this process. We get epsilon 0, which is the limit of omega to the power of omega to the power of omega, etc. And then we keep going and reach epsilon 17 and lots of these things, right? So we have this intuition of what an ordinal is, but it's a bit vague. So you could ask for a formal definition. And of course, classically, the answer is something like this, that an ordinal is a set with an order. So that's important for the ranking. And this order needs to satisfy certain axioms. So there's many ways to do this classically. Here's one way. You could ask for it to be transitive and well-founded, meaning that you can't have an infinitely descending sequence. And you could ask for trichotomy, that is, you can decide if A is smaller than B, or A is equal to B, or A is greater than B. But of course, trichotomy constructively is a terrible axiom. That's far too strong for ever to be useful. So we probably at least want to replace that with extensional, saying that if two ordinals have the same predecessors, then they are actually equal. Right? So that's one definition, but it's also perhaps not a very good one because it's hard to use. So you could say, okay, we don't just study ordinals for the sake of it, just because classical set theory introduced it. Perhaps more importantly is to ask, what do we want to use ordinals for? So let me give you two examples where ordinals are actually useful for doing mathematics. So the first one is one of my favorites because I like initial algebras. So if you have a finitary functor, let's just say on set to be simple. So finitary here basically means that if you give the functor a finite set, then you get the finite set out again. Right? Then you can construct the initial algebra of f by taking the co-limit of a certain sequence. So you start with the empty set, so that's your x0. And then if you don't want x0, but you want xn plus 1 for some n, then you just apply f to the previous stage, right? So you do this, okay, but you want this to be a sequence, so you need maps between them. So you need a map from x0 to x1, but there's one unique map from the empty set to any other set. And then once you've started, you can just apply f to the previous map in order to keep going, right? And if the functor is finitary, then once if you just take the co-limit of all these finite stages, then by definition, finitary means that it's going to preserve this co-limit, and we have found our initial algebra, right? So basically, you take the union of all the finite stages, and that gives you the set that is the initial algebra of the functor. So that's all well and good if the functor is finitary. There's nothing complicated going on. But of course, the functor might not be finitary. It could preserve some larger co-limit, some kappa co-limit. And then classically, there is no reason why we couldn't just keep going, right? So we reach stage omega by taking the co-limit of all the previous stages, but then we can again apply the same equation here in order to get the next successor stage. It didn't matter that this alpha used to be a finite n. This works for any ordinal, right? We just apply the functor to the previous stage, and that gives us the next stage. So this way we can go past omega, and whenever we reach a limit stage, again, it didn't matter that this was omega as such. We could do this for any limit stage. We can just take the co-limit of all the previous stages, and that gives us a new object, and then again we can keep going. And eventually, if we do this kappa many times, then we're going to find the initial algebra again. So here we could use the ordinals to actually construct the initial algebra of the functor f. And if the functor was not nice enough, then we needed to go beyond the finite ordinals in order to do it. So the thing that was useful here for the ordinals was that we had a definitional principle where we could define something by saying what happens if it's 0, what happens if it's a successor, and what happens if it's a limit. And that this actually was a well-defined definition, right? And here's another example of where ordinals can be useful. If you have some process that you want to prove actually terminates, so for example, you have some imperative program like Turing did in 1949, or you have some proof of some proof system, for example, the proof system PA, you want to show that cut elimination terminates, or you have the Goodstein sequence, which is this number theoretic sequence, which seems like it shouldn't terminate, but it does, or you have the Hydra game. So let me tell you about the Hydra game as a fun example. So this is a Hydra, it's a tree, not a binary tree, but you say I can have arbitrary branching at each node. And the point of the game is to remove all of the heads of this Hydra. So think of the leaves of this as heads, and I want to cut off some branches. And if I cut off this branch, then it just dies, and I can remove it, and it keeps going. But if I cut off a branch which is not at the root, so I cut off this one, then the rules of the game says that I should go down one step, which is something I couldn't do at the root, so that's why that's the base case, right? But here I go down one step, and then I make n copies of the remaining subtree root of that place, where n is the round of the game. It's other variations where you don't have this multiplying factor, but it doesn't matter. So let's do it as hard as possible. Where I make, this was the third stage, so I make 3 copies of this thing. So I've replaced this one head with 2 more heads and lots of subtrees in between, right? So it might seem like it's very unlikely that this process will ever terminate, because after all, I just removed one thing and I made many more things, right? And in fact, what the point of introducing the game by Kirkby and Ferris was to prove that you can't prove that this terminates just in Peano arithmetic. You need to go beyond Peano arithmetic to prove that this process terminates. And the trick to do it is to assign an ordinal to each node in the tree. So you assign 0 to the leaves, and then when you have a non-leaf, then you take omega to the power of the previous thing. So omega to the 0, that's 1. Omega to the 0, that's 1. And then you add it all up. And let's ignore the order of how you add things up, because let's just pretend you do it in the order that makes sense. So here you get 2. Then here you only have 1, so you get omega to the power of 2. Here you get omega to the previous 1 plus omega to the 0, etc. So that gives you an ordinal for the root in the end, right? And then you observe that cutting off a head like this is going from an ordinal omega to the power of 2 to, in this case, omega to the times 3, which is a smaller ordinal, right? So even though you've increased the number of heads, you've actually decreased the ordinal associated to the node. So that means that when you do this, you cut off things, then in the end, you get a decreasing sequence of ordinals. And then one of the axioms we had for ordinals was that every decreasing sequence must terminate in a finite number of steps, right? So that's one way to prove that this process actually terminates. So the thing that was useful in this example was that, well, first of all, we could do arithmetic on the ordinals, so that we had a way of combining the things together, and that every decreasing sequence must hit 0 at some point. And of course, we want this in the strong sense of actually finding a natural number where this terminates, right? We don't just want to know that it's impossible that it can't terminate, because we don't want to use Markov's principle in order to actually find a termination witness. So we'd like to have this in a very strong sense that we can calculate a particular index in the sequence where we hit 0. So a problem or a feature in a constructive setting is that different notions of things are actually different, right? So that's sometimes annoying, but it also makes life interesting, right? So the classical definition of ordinals that I gave you in the beginning, transitive, extensional, and well-founded, is not particularly well suited for either this iteration principle or determination. Right? So determination was okay, but it's usually formulated negatively so that we don't actually find a witness. So what I want to consider today instead are three more or less known notions of ordinals that I've been considering in computer science and how they can be used to do these useful things instead. So these are Counternormal forms, Brouwer trees, and well-founded extensional transitive orders. So I'll talk through these in turn and explain what they are. So they're quite different notions. So it's just interesting to consider what makes them the same and what makes them different, and why we feel justified in calling them all ordinals and not just wildly different things. Right? And one of the morals of the talk is that you really need the features and concepts of homotopy type theory to do this correctly in type theory. So you need quotient inductive types and, well, at least baby versions of univalence, such as propositional extensionality, in order to get the right thing. So that's not something I know to do in general in ordinary McIntyre type theory. So even if using function extensionality and things like this. So let's start with the simplest and most down-to-earth notion, which are the counternormal forms. And this is, like many of these notions, are motivated by a classical theorem. So we take a classical aspect of ordinals, and then we turn it into a definitional principle instead. So the classical theorem by Cantor says that every ordinal can be written uniquely as a finite sum of powers of omega. So, and uniquely is the important part here, right? And it's unique if you insist that these exponents are actually decreasing. Right? And if alpha is small enough, so if alpha is smaller than epsilon 0, then all of these betas are also smaller, which gives you a way to represent an infinite ordinal in a finite way, right? Because you take a large ordinal and you write it in this form, and then you recursively do the same thing for all of the exponents. And then again, here you have a process of ordinals that get smaller and smaller, which means that this process must finish at some point, which means that you bottom out and you have a 0 of one of these. So 0 is, of course, the special case, but when you have no exponents at all. So you could, in this way, you could see every alpha if it's smaller than epsilon 0, otherwise it doesn't work, then it doesn't decrease like this. But if it is small enough, then you can see every alpha as a finite binary tree like this, right? Where you take all the exponents and you convert them into binary trees until finally you hit 0, and that's the one. So you can represent an ordinal as an unlabeled binary tree, where I have a leaf, which I'm going to write as 0, because that's how I think of it. And I have a node, which has two subtrees. So the first one represents the exponent of the first thing, and the second one represents the rest of the tree. Right? So I'm cutting this thing here. I'm saying this is my first thing, and then all of this is the rest of my tree. So all my trees are going to have this shape, more or less, right? Except I can, of course, nest them inside these things. Okay, but if I do it that way, then I haven't captured the uniqueness of the fact that all of these exponents has to be decreasing, right? So I can do that as a separate type. So that means that first of all, I have to define an order on these trees, and I just do that lexicographically. So I say that 0 is smaller than everything, and if I'm comparing two non-zero things, then I first compare the first exponent, and if they are equal, then I keep comparing the rest of the trees. Right? Okay, and then later we will see that this is a sensible notion of order on these Counternormal forms. So we can define a predicate which expresses that if I have one of these, then all the exponents that occur are decreasing like this. And then I can define my type of Counternormal forms to be a tree together with a proof, which says that it is in normal form. And you can prove that firstly, this order is propositional. And secondly, that this predicate is here in F is also propositional. So this really is a subtype of all the trees. And for equality purposes, the only thing that matters is the tree. Right? It can't be different proofs. Here are some basic properties of this type. So the way I describe it, we first described all the trees with lots of junk, things that are not in Counternormal form, right? And then afterwards, we had a predicate to single it out. But you could also define it inductive-inductively. together with the less than relation. And then you insist that when you form this tree, then the first exponent of this has to be smaller or equal to this one, right? So that you don't introduce any junk into your terms, but then there has to be an inductive-inductive definition, because you have to define the trees and the order of the trees at the same time, and they are both defined inductively, right? But I think that's quite a nice way to do it, because then you always know that things you're working with are well formed, and it suggests lemmas for you that when you try to define operations on these things, then you need to make sure that you preserve this relation, and that's the lemma you have to prove afterwards. So on the other hand, you have to use induction. So this is a little bit more down to earth and basic. Right? It's just the sigma type in the end. Or if you want to be fancy the other direction, so this is just induction. There's not quotient induction. But you could also use quotient induction to define multisets. So sets where you can have more than one occurrence of the same set, but the order in the set doesn't matter. So you define it as lists, and you quotient out by permutations, basically. So you have multisets of these exponents, and that's another way to make it unique, right? So the important part is the uniqueness, because otherwise you will have this condition here ensures that there's only one way to represent each ordinal. And that's what makes it work. And another way to make it work is to just quotient out the difference. Okay, so you can define it any way you like, and they're all equivalent. So by univalence, they're all equal. So that's nice. But any way you do it, you can prove that the order here is actually trichotomous, which is this thing that I said was too strong before, right? But because these are very concrete, very syntactic entities, you can just look at them and I mean, they're all first order, so you can just compare them for equality and actually decide if x is smaller than y or if x is greater or equal to y. Right? Where greater or equal to is just defined to be greater or equal, literally. And we can get away with this naive definition because these are such simple things. And then as a simple corollary, that means we have decidable equality, right? Because we can also show that this order is irreflexive. So if we want to decide if x is equal to y, then I can just check if one is smaller than the other or not. And if they are equal, then I'm happy. And in all other cases, they must not be equal, because assuming they are equal would lead to a contradiction with the fact that I would say that x is smaller than x, right? Which is not true. And this is where it gets a little bit interesting, I think. So that so far, that's all well and good, and you don't really, I mean, it's not surprising, but because we've insisted on these representations being unique, we can actually prove transfinite induction for these counternormal forms. So meaning that if we have any predicate of these, and assuming that we can prove p of x, assuming we know that p of y holds for everything that's smaller, then we can show p of x for every x. Right? And again, uniqueness is what makes this work. Otherwise, it wouldn't work. And it's perhaps also not so surprising that we can classify these things as zero, successors, or limits. So zero and successor, that's kind of clear, right? Limits is perhaps a little bit more surprising, but it works because for these simple counternormal forms, everything that's not a zero or a successor must be a limit, which might not be true constructively in general. But we can't compute the limits. So if you give me a sequence of counternormal forms, then I can't actually say which counternormal form this converges to, if anything. So there's a boring reason for this, is that you could actually take a limit of a sequence which goes beyond epsilon 0, which is the upper bound of these. But there's also a more interesting reason, which is that if you could do it in general, even for bounded sequences, then this would imply the weak limited principle of omniscience. So you can decide if a sequence has a 1 in it or not, if you could do this. So that's not possible. But we can still classify them as a limit, even if we can't compute the limit. Okay, so let's consider another variation, which is also quite well known from before HoTT, I think. So this is the idea that an ordinal is something you get if you take the ordinary natural numbers, so 0 and successor, and then you throw in one more constructor, which is the limit constructor or the supremum constructor. We say that if you have a countable sequence of ordinals, then you should be able to take the limit, right? So this looks a lot like the thing we used for the transfinite iteration, right? Where we said that, well, an ordinal is either zero successor or a limit. So that a priori looks very nice, and it's something you can do in, I mean, it's a common exercise in independent type programming to work with these things and define addition and things on them. But unfortunately, it's a little bit of a lie that this sup constructor really is the sup constructor, right? Because, for example, if you look at the sequence 0, 1, 2, 3, etc., then you would expect that the supremum of this sequence should be the same thing as the supremum of the sequence 1, 2, 3, where you just omitted the first element. Doesn't matter. It shouldn't matter if you start with 0, if you start with 1. These should both reach omega anyway, right? And similarly, if you look at the sequence 0, 1, 2, 3, and you look at the sequence where you swap the first two elements, this also shouldn't really matter in which order these appear, because the supremum of these sequences should both be omega again, right? But because this is just a constructor, this is an inductive type, then these things are actually not equal, right? Because they are the same constructor applied to different things. And by the rules for inductive types, the same constructor applied to different things is never going to be equal, right? I mean, that's why suc of x is not the same as suc of x, for example. So this naive definition of ordinal trees is not a very good one if you actually want to represent ordinals. So how can we fix this without losing the nice properties? So as an inductive type, this is obviously well-founded, right? Because it just has the subtype ordering, etc. And it's obviously the case that we can classify one of these as either 0 or successor or supremum. I mean, that's exactly what the induction principle for this one says. So here is how we try to fix this. So now this time we define a quotient inductive types. So now I don't think you can get away with doing this any other way. And I'll tell you why in a second. So it's the same idea. We have a 0, a successor, and a limit. But for the limits, we first of all insist that the sequence is strictly increasing. So we just call it increasing, but we know that it means strictly increasing for an order that we're now going to simultaneously define. So that takes care of this problem here, right, where the order of the things ruined things, because now this sequence here is not strictly increasing anymore because 0 is not strictly greater than 1, right? So I'm not allowed to have this one. And in general, it also takes care of the problem that you can have the supremum of a constant sequence if you don't insist on these things being equal. And then you can't tell if that supremum of the constant sequence, if that's actually equal to 0 or a successor, right? So you would lose classification if you didn't insist on strictly increasing sequences. So that's one thing we do, but it still doesn't take care of this problem that it shouldn't matter if you insert something else here, right? So we also quotient this type in a quotient inductive way by saying that bisimilar limits of bisimilar sequences are equal. So the limit of f is equal to the limit of g if f is bisimilar to g. And by bisimilar, I mean that f is simulated by g. Sorry, it's a copy-paste error. It should be f is simulated by g and g is simulated by f, right? So it's both ways. Where f is simulated by g if for every I there exists a j such that f of I is smaller than g of j, right? So I can always find something above. If I want to look at f of I, then I can always find some index where g of j is above it, and conversely the other way around, right? So they really are simulating each other. And so for example, this sequence should be bisimilar to this one, right? Because after this first index, they are the same. And for this one, you can find that 1 is greater than this one, etc. So we quotient by this, but that means because this notion here refers to the less than relation, that means that we have to define this at the same time, just as for the increasing, right? So we have to give some reasonable definitions. So we say that 0 is less than or equal to x, and we throw in transitivity because we are going to prop truncate this anyway, just like we are set truncating the type. So otherwise you could worry, maybe we can define transitivity from the other ones, but in practice, since we are prop truncating, it's not a problem to throw it in. I mean, it could still be a problem because it could make our inductions harder, but in practice, it doesn't seem to be, so we're happy to throw it in. I don't know if it follows from other things. We weren't able to prove it, so probably it doesn't, but who knows. So anyway, transitivity, we throw in that the successor function is monotone, so it preserves the order, and we have two constructors that tells us what limits are. Right? So the first one says that in order to be smaller than the limit, it's sufficient to be smaller than some particular element of the limit, because we know that all of the elements are going to be smaller than the limit in the end. And in order to be greater than the limit, it really has to be that you're greater than all of the elements, right? And notice this is smaller equal, so that's why all of this makes sense. And then we define x to be strictly smaller than y if the successor is the smaller or equal to y. And that's the notion we use here in the increasing, so they're strictly increasing sequences. And note that this is really a quotient inductive type in the sense that the limit constructor here is infinitary, right? So it doesn't really work to first define this type without the path constructor and then later quotient it, because then you run into these well-known problems about countable choice in order to do it. So it really has to be quotient inductive all at the same time. Okay, so we have this definition of the less than relation, but it's not very easy to work with, right? Because, I mean, partly because if you do this in Agda, then Agda is not as clever as it could be about ruling out impossible cases, but also you would like to know that, for example, if the only way that you can be smaller than a limit, for example, is by using this constructor, right, or transitivity. But the only way that you can introduce some evidence that you're smaller than a limit is to use this constructor. So you could expect to actually know the k whenever you know that something is smaller than a limit, right? And that's what you need in order to work with this concretely. But you don't get that immediately from this definition, right? So what we do is we use an encode-decode proof in order to characterize exactly what it means for x to be smaller or equal to y according to this definition. So we define a code predicate, which takes two Brouwer trees, and we make sure there's propositional, otherwise they have no chance of doing any of this. Well, nothing else because we want to have this equality, but of course we want it as an equality from propositional extensionality, so we just want maps in both directions. But because this is a proposition, if we want them to be equal, then this better be a proposition as well. So we want to characterize code in this relation in this way, and then of course we want to add in the sensible cases. So for example, here is what it means to be strictly smaller than a limit, right? Because remember that we said strictly smaller is defined to be suc of s is smaller or equal to. So we say that x is strictly smaller than a limit if there exists an n such that x is strictly smaller than f of n. So this is our wish for what it should mean. And then we work hard and we prove that we actually have this equality, right? And it's quite technically involved because everything is simultaneously defined. It's not enough to just define this, and then afterwards you can just prove the equivalence, because, for example, these limits have to be increasing. We at the same time need to prove that code is transitive and that code is reflexive, and even one of these directions of the definition simultaneously with the definition of code itself. Right? So it was surprisingly involved, and it took us quite a lot of tries to get this right. But after you've done this, you're through the mystery, then everything is great, and you can prove lots of nice things about Brouwer trees. So for example, the order is well-founded and extensional, which if you just try to do it naively, by induction on the constructors of this type, then I think you have no chance whatsoever. But after you characterize it like this, then it's I wouldn't say it's a breeze, but it's much easier, right? And one thing that is going to turn out to be quite important is that even though we can't decide equality in general, so that implies Markov's principle, we can decide a limited form of equality. Namely, we can decide if a tree is 0 or a successor of 0 or a successor of 0, etc. Right? And that's exactly because we insisted on increasing sequences here, right? So we know that a limit is not equal to a successor, for example, and that will turn out to be really important. So it's not something you think of at first, I think. So we tried without this for a long time, but we couldn't make anything work unless we really had this classification result. So right. So but yes. So you have this limited decision that you can decide if something is finite. But of course, you can't decide if two limits are equal to each other, because that would be like deciding if two functions are equal, right? Or simulate each other at least. So even not stability of equality, which is slightly weaker, even that implies Markov's principle already. So there's no hope of this. But then, so this is the nice thing, I think, that's a little bit surprising. So you have this still quite naive looking definition of an ordinal, right? That's a 0 successor limit. And then you throw in this bisim constructor. And then all of a sudden, so it's well-founded, but that's not so surprising. It was well-founded already. But all of a sudden, you can prove all of these equations that are really not syntactic equations that you would expect, right? So for example, n times omega is equal to omega. And if you have something which is smaller than the power of omega, then adding them together, so I'll talk about addition in a second, but if you believe me that you can define addition for now, then you really have that these things are additive principal ideals, and you can construct the limit epsilon 0 like this, of course, and you can prove that it's actually a fixed point, and so on. So you really start to see these things as having the real properties of ordinals that you expect. And I guess you had some of this also for the Counternormal forms, but they're so syntactic that you don't really expect it, I guess, or you feel like it's cheating. But these things really have the expected properties. And the last type of ordinals that I would like to talk about is the extended well-founded orders that some of you might remember from the HoTT book already, right? And these are, of course, directly inspired from the classical definition, or at least via Paul Taylor's version, where he's replacing trichotomy with extensionality. Right? So transitivity, as you would expect, extensionality, elements with the same tree sets are equal, and how do we formulate well-founded? So this is maybe one point that's important to dwell on. So it's not this negative formulation that there can't be any decrease in sequences, but rather we have this positive formulation due to Peter Axel, where we say that every element is accessible, where accessibility is this inductively defined notion, which has one constructor, and it says that X is accessible if every Y smaller than X is accessible. And then, of course, the base case is if you don't have any Y smaller than X. So that's the nice positive way to formulate well-foundedness, also in the HoTT book. And Martin Escado has done a lot of formalization of these, which is great. So that gives us a type of ordinals, right? But it's easy to be fooled by the fact that they themselves have to have these nice properties, and they have an order. It's easy to forget that we also now need to define an order on the type of ordinals themselves, right? So if I have an ordinal X and an ordinal Y, they come with their order relations. I have to define what it means for X to be smaller or equal to Y. And here's the definition from the HoTT book again. So they say that X is smaller or equal to Y if there is a monotone function from X to Y. So it needs to preserve the order with this simulation condition. So this says that if Y is smaller than f of X for some X, then we can pull X back to some X0 such that f of X0 is equal to Y. So if we have an inequality in y, then we could pull that back to an inequality in x in this way. And we call this F simulations. And it will turn out that this is also a propositional notion, which is, of course, not at all obvious when you first see it, because you might think that there can be many monotone functions from x to y, but this simulation condition makes sure that it's propositional as we want. Right? So that's what it means for x to be smaller or equal to y. What does it mean for x to be strictly smaller than y? Well, for that, let's define the part of y which is below little y. So this is a sigma type of all y prime such that y is smaller than y. So this is the initial segment of y below y, right? Because everything in this type is smaller than y. And then we say that x is strictly smaller than y if there exists a simulation as above, such that further there is some y in y such that f factors through this initial segment. So x has to be isomorphic to an initial segment of y, and this simulation has to factor through it. And we call this a bounded simulation. So these are also the usual classical definitions, I guess. So they look a little bit more involved than the other notions because they come from classical mathematics, I suppose. But okay, so we have this definition, and then again, we can prove that this order is extensional and well-founded. Right? So in other words, the type of ordinals, well, okay, you can also prove this transitive. So the type of ordinals is itself an ordinal in the next universe up. Right? So that's how we avoid the usual Brouwer-Forty paradox, that the type of ordinals is an ordinal by universe levels. And okay, so it's not so hard to see that you can, that there is a zero, that's the empty type, and there is a successor, that's basically co-product with one. But it's perhaps a little bit more surprising that you can actually compute limits of sequences here, which you basically do with a sigma type. But it seems like you can actually only do this for increasing sequences. So again, if you don't restrict the increasing sequences, then you can't show that the thing you produce is actually a limit in a notion that I'm going to tell you about soon. And here's, it's not a theorem, but it's a meta theorem you're tempted to state after a while, which is that nothing is decidable for this notion of ordinals. So for example, you can't even decide if an ordinal is a successor or not without implying it's through the middle. So in terms of working with these, they're really terrible. And I guess Martin should have a lot of kudos for pulling through and formalizing so much and doing so many interesting things with them. But I think for the working constructive mathematicians, they're not great to achieve other things. I think that the thing that's really good about them is that they obviously correspond to the classical ordinals, right? Because they have the same axioms. So in order to compare with classical results, then they're obviously the right thing. So that's the main merit I see from them. And if you like proving that things implies constructive taboos, then they're a great source of that as well, of course. But, okay, so we have these three different notions, and they're all very different, right? So one is very syntactic, the other one has this nice inductive flavor, and then we have this more classical flavor. And why are they all ordinals? Why have I called them ordinals? So in order to answer this question, we try to introduce an abstract framework and see what we can do abstractly without focusing on a particular type. Right? So we already know that all of these have an order relation, which is propositional, extensional, and well-founded. I guess that's the least you would expect. So now let's assume a little bit more in general. So we have some set, we have two relations, and they need to be related in certain ways here, but we're not assuming that this, for example, is the strict relation or they are equal. These are just two completely different relations. And then we need to assume some things in order to get any results at all. So we're assuming that the strict relation, which of course this is just a relation, I'm calling it the strict relation because of intuition, but so far it's just some relation. So the so-called strict relation needs to be transitive and irreflexive. And the non-strict relation needs to be transitive, reflexive, and antisymmetric. So if x is less than or equal to y and y is less than or equal to x, then they have to be equal. And the smaller one needs to be included, the strict one needs to be included in the non-strict one. So that means that if x is less than y, then x is less than or equal to y. And we need a kind of a form of mixed transitivity where if x is less than y, and if y is less than or equal to z, where again, I don't mean less than or equal, but that's just the name I use, then overall x should be less than or equal to z, right? So it's like mixed transitivity. One is strict, one is non-strict. And it's really, yeah.
The right-hand side, you mean x less than z, right?
X less than, yes, I mean strictly smaller than z. Yes, thank you. Yeah, because this is strictly smaller, right? Which is as it is here. Okay, and it's really tempting to think that it should work the other way around too, right? Where you just say that first x is smaller or equal to y, and then y is strictly smaller than z. But if you insist on this, then you just thrown out the ordinals from the hotbook, because having this for those is equivalent to having excluded the middle. So that's it's a bit surprising. That, I mean, it seems so innocent to just swap the order, but it really makes a difference. I think this is one of the reasons why Paul Taylor introduced the Plamp ordinals to get this for that subclass of ordinals. But so we have to make sure that we only use this form of mixed transitivity. So for Counternormal form, for example, we also have this one, of course, but for the more undecidable notions, we can't afford this. Okay, so we have this abstract setting. We assume these things of our order relation, and then we can try to see if we can formulate the notions of an ordinal in this way. So the first thing we can say is that A is a 0 if it is the smallest element, right? So every B is greater or equal to A. That's perhaps not too surprising. And similarly, we can say that A is the successor of B if it is greater than B and it is the least element which is greater than B. Right? So it's the least upper bound of B. And we say there's a strong successor if B is the predecessor of A. So conversely, which does not follow from this. And we can say that A is a supremum of a countable sequence of elements if it's the least upper bound again. Right? So, but this time formulated using the non-strict inequality. So it's an upper bound. It's greater or equal to all the FIs, and it's the least one. So if anything else is greater or equal to all the FIs, then A is less than or equal to X. So it's a lot like the successor case, but for a whole sequence and for the non-strict version. And then we say that A is the limit of F if the F is also increasing, strictly increasing. So that in particular means that it's actually going to be strictly above this, right? Because it's if it's greater or equal to one of them, then when you go to the next one, it's going to be strictly greater. And then you can look at these notions, so you can see what happens for the different notions of ordinals that we have. So they all have 0 and strong successors, and these are unique, so that there can be at most one 0 and strong successor for all of these ordinals. And like I said before, Counternormal forms cannot compute limits, right? So it's just not the case that we have them. There is a limit for every F for Counternormal forms, but for Brouwer, this is by definition. And like I said, for hotbook ordinals, this works as long as the sequence is increasing. So that's why we have this definition here. And for Counternormal forms and for Brouwer trees, we can decide for each ordinal if it's a 0 or a successor or a limit, like I said. But for the extensional well-founded orders, this would again imply lower excluded middle. So it's just not, like I said, nothing is decidable for book ordinals. And so that concretely, you can try and prove this for each one separately. And again, these are separate proofs of common properties, right? But abstractly, you can also show that this type of classification of being either a 0 or a strong successor or a limit is actually a proposition. So that means that you can't be a 0 or a successor at the same time, right? Because if you were, then this would not be a proposition. So that implies that if you have classifiability induction, meaning induction in the classical sense, where you have to give a case for zero, you have to give a case for successor, and you have to give a case for limits, then because this is a proposition, so by induction, I mean just a propositional predicates, by the way. So because this is a proposition, we can use that to prove that we can classify it, right? And conversely, if you can classify things and you have well-founded induction, then you can also do classifiability induction. Right? And this is in the abstract setting, so it doesn't talk specifically about CNFs or Brouwer or book ordinals. It's just the fact that from these previous axioms about the order and these definitions of what it means to be a zero successor limit, you can show these things. Okay, so the reason why we want to introduce these abstract notions is that we want to talk about arithmetic on ordinals. And of course, if you only have one notion of ordinal, like in classical set theory, then you can use the uniqueness of transfinite recursion to show that any notion of addition must satisfy these three equations. So if A is a zero, then C plus zero should be equal to C. And if A is a successor, then C plus a successor of B should be the successor of C plus B, right? But we have to take care to formulate these things relationally, because there might not in general be a function which computes the successor of a given ordinal, or there might not be a function which computes the limit of a given sequence, right? So here we say that A plus a successor is a successor of A plus the predecessor. And here we say that if A is a limit, then C plus the limit is equal to the supremum of this sequence, C plus all the FIs, right? And here we choose to have a strong notion of limit when we start, but in the conclusion, so it looks like this is not in the conclusion, but this is of course talking about the B here. It's not clear a priori that this sequence is actually increasing, so it doesn't make sense for this to talk about limits. It just has to talk about suprema, right? Okay, so this is what it means abstractly for one of these structures to have addition. There should be a function which satisfies these three specifications. And then we say it has unique addition if there's exactly one function that does it, right? And concretely, we can show that Counternormal forms and Brouwer trees have unique addition, and ordinals has addition. It's probably, I mean, classically it's unique, of course. Constructively, we don't know that it's not unique, but we haven't been able to prove it. And let's just look at the Counternormal form version. So this is how it typically goes, right? So it's a more or less standard definition where we say that 0 plus B is B, A plus 0 is A, and if they are both non-zero, then we have to check if this exponent is smaller than B or not, because remember that we have to have these decreasing sequences. So if this exponent is smaller, then we can just throw away all of the first part and just keep the second part. And if not, we can keep it and keep adding, right? So we define this thing on the various syntax. And then afterwards, of course, we have to prove that this notion of addition actually preserves being a normal form, which requires some lemmas about what's happening in these cases. That if you do it inductive-inductively, you get thrown in your face what you need to prove. And what's perhaps a little bit less standard is that in order to prove that it actually satisfies this specification, then we have to define, well, we do define subtraction that works the other way in order to get the right thing, right? So note that even though we can't compute limits, we still satisfy the specification that we compute the right thing if A happens to be a limit, right? So we can do this. We can satisfy the specification even if we can't compute the components. Okay, so once you have addition, you can play the same game for multiplication, assuming that you have addition, and it's the same deal. So we say that this abstract structure has multiplication if C times 0 is 0, C times a successor is C times the predecessor plus C, and c times a limit should be the limit of all the things again. So nothing too surprising here. And concretely, you can again show that CNF and Brouwer have unique multiplication. And again, classically, odd should have unique multiplication, but constructively, we've only been able to prove that it has multiplication. But, so here's one little subtlety with Brouwer trees, where seemingly you would have a straightforward definition just following exactly these specifications, right? It's telling you what to do with a zero, what to do with a successor, and with a limit. So you would think that you could just say x times 0 is 0, x times a successor is the right-hand side it had to be, and x times a limit has to be a limit of the things. But there is a problem if you try to do this, which is that all our sequences had to be increasing, right? But in particular, if x is 0, then all of these elements is just going to be 0 times fi, which is going to be 0. You can prove that 0 times x is 0, just like x times 0 is 0. So that's not going to be an increasing sequence anymore, even if f started off being increasing, right? So this definition just does not work. But thankfully, we could exactly decide if a Brouwer tree was 0 or a finite successor, right? So we can just do that. We decide if x is 0 or not. If it is, then 0 times anything should be 0, so we can return 0. And if not, that's exactly what we need in order to prove that this function here is increasing, right? Which, again, we have to do it simultaneously. So it turned out to be really important that we could decide if the Brouwer tree is 0 or not, which a priori you might think that it doesn't really matter. But it didn't seem possible to actually define multiplication otherwise. Okay, and then you can do the same thing with exponentiation, where in this case, because exponentiation is a little bit special in that 0 to the power of 0 should be something, etc. So we have to split up the limit case to if c is 0 or not. And here, concretely, it's not so hard after you've done all the code and encode decode stuff to show that Brouwer has exponentiation. For CNFs, it's not so hard to do. Well, base omega is basically by definition, right? And you can write the right implementation for other bases, but in order to show correctness, you would need to define logarithms, which I don't think is there's any technical reason not to do it, but it gets a bit hairy, so we haven't done it yet. So let's just see if we can summarize how all of these different notions are actually connected. So we have the three different notions. We have Counternormal forms, Brouwer trees, and extensional well-founded transitive orders. And in general, things here are decidable, things here are undecidable, and things here are partially decidable, right? In the sense that we can decide some things. And of course, if you have a counternormal form, then you can quite easily translate it into a Brouwer tree by sending 0 to 0 and sending something of this form to the corresponding things over here in Brouwer trees after you've defined exponentiation, omega to the power of, etc. Right? And then again, if you've done your encode decode homework, so you have all the nice facts about the order here, then you can show that this map is injective, and that it preserves and reflects the orders and commutes with all the arithmetic operations. And of course, like we said, epsilon 0 is not representable over here, but it's easy to represent it here as a limit. So you can show that this map is non-surjective in the sense that it's bounded by epsilon 0. Right? You can't go beyond epsilon 0. So the Brouwer trees are strictly larger than the counternormal forms. And similarly, you can go from a Brouwer tree to a book ordinal by sending the Brouwer tree to all so it has to be a order. So we send it to all the Brouwer trees which are strictly smaller than a, right? So it's the initial segment by a here again. Right? And you can show that this is injective and that it preserves the order. But when it comes to the arithmetic operation, it's a little bit harder to show an equality, but one direction is okay to show. So you can show that, for example, if you translate x plus y, then that's at least greater or equal to the translation of x plus the translation of y. Right? Again, I think classically there's no reason why this should actually be a strict inequality, but and it commutes with limits, but surprisingly, the fact that it commutes with successors is again a constructive taboo. Right? So, and if you think about it, so this is an ordinal one level up, and of course this is a type which has a well-founded transitive and extensional relation, so it's also an ordinal one level up, right? And now here we have a monotone map between ordinals. So you could ask the question if this map is actually a simulation, meaning that it would show that Brouwer is actually smaller than this, right? And if you have excluded the middle, then you can show this. But unfortunately, if you can show this, you also get something non-constructive, and you get WLPO again. So it's just not. It's classically true that it's a simulation, but constructively it's just not possible to show. Okay, and again, this, because we said that this was an element here, then of course this map is also bounded by Brouwer. Otherwise, we would have the Brouwer-Forty paradox. So again, there are things here in odd which you can't represent here. But no matter where you start, you can always translate it here to the type of ordinals that looks like the classical ordinals, which tells you that they are the real thing in some sense. Right? But I think one moral of the story is that if you actually want to work with these things, then it's better to work in the lower cases where you can. So for example, you could work with Counternormal forms in order to prove termination, and you can work with Brouwer trees in order to do iteration. And then in the end, if you have to, you can embed it into the type that classical mathematicians like to think of. But it's much harder to work here directly. It's better to carve out a nice little place where you can actually do things. Okay, I guess that's basically what I said here again. And of course, there's lots of future work. So these are quite naive, easy first cases of ordinals you can consider. But of course, there's many other ordinal notations. So the Veblen normal form will be a basic one to go beyond the Counternormal form, for example. And Javel has some nice combinatorial types of trees that are quite clever, that can get you a lot further, but are a little bit tricky to embed. And of course, I also said that this thing in the middle was partially decidable, right? And I think we can make that a little bit more precise by working with semi-decidability and show that many things there are actually semi-decidable, meaning that you can get, intuitively, you can get a yes answer, but a no answer might run forever. So it's not the whole story. So it's not the case that inequality, for example, is semi-decidable in general, but low, I think, inequality for ordinals, Brouwer trees, less than omega square or something like this is actually a semi-decidable. So there's something like that there. And if you want more details, then there's a paper you can look at, or you could just look directly at our cubic Hydra formalization, where we have most things except for the book ordinals that Martin has done so nicely for us already. All right, thank you very much.
Okay, thanks. Let's all silently applaud the speaker. And if you have a question, just go ahead and unmute yourself. Hey, yeah, go ahead.
I have a question. So if you go back to the slide where you were comparing those to the three notions of ordinals with the embeddings there, that the one on the right, the embedding, does that get better behaved if you use the plump ordinals as the codomain?
That's an interesting suggestion. Right, because it's indeed it should lie in there. Yeah, we haven't. So yeah, let's look at that. That's a good idea.
I have a question about this slide also. The very last thing on the slide, you say the right-hand map is bounded, but I'm a little confused because the type of Brouwer ordinals isn't a small type, so it isn't one of the ordinals in the right itself.
Right. So I guess that's a little bit fast and loose indeed. Yeah.
So, I mean, maybe, do we even know if it really is bounded?
Why isn't it a small type?
Oh, yeah. Sorry.
Oh, is it?
The Brouwer is a small type. Yes. So
okay, sorry.
so that lives in the lowest odd over here. It's just because the elements of Brouwer, this is inductively defined. So yeah. So
You only took suprema limits of countable sequences.
yeah, yes. Right.
Okay.
Yeah.
Okay.
Yeah, you could of course consider arbitrarily set index sequences, and then it wouldn't be then it would be large again, right?
Okay. So you're only getting countable ordinals then in the middle one.
Yes.
Okay. So the left one you're getting up to epsilon naught. The middle one you're getting more probably.
Yeah.
You, for example, get epsilon naught, but you're still only in the countable ordinals.
Yeah.
Okay. Thank you. That clarifies it.
If you do this classically, do you get literally all the countable ordinals in the middle?
Yes, I think so by Kleinius argument, right? Because
I guess a related question, is the first inclusion a simulation?
That's also a good question that we haven't considered. It's plausible, right? Because everything is so nice and decidable. Yeah, it's a good suggestion. I don't know the answer, obviously. But.
Hi, I have a question about this slide as well. Does the WLPO imply the B2O being a simulation, or is it no? I know it's not on the slide. I'm just wondering how much is known about this.
Right. So yeah, we don't. Yeah, I mean it's an obvious question / criticism, right? That there is a gap here, right? And it's the best we could do. So we haven't been managed to prove that WLPO implies that BTO is a simulation. But needed to use a stronger principle. But it's open if what happens in between there.
Another question about the Brouwer trees. Related to just what we were talking about. So you take limits of countable sequences. Could you do something where you allow the sequences to be indexed by ordinals that you've defined already?
Yeah, I've considered this at some. I think that's doable, right? I mean, might be an induction.
So that would include successor sort of automatically, or I guess. Zero. Zero would be the limit of the
right,
sequence, and successor would be the limit of the identity map.
Yeah, yes. My experience is that you really want these things to be increasing still. So that would. Oh no, that would right. I see. Yes. So you mean okay? So 0, yes, and then successor. You're saying.
Well, actually, I'm not sure about successor, but anyway,
yeah, I mean it
the
might just
being you
push
allow
get you
yourself to get
further.
uncountable things. Right? Sorry.
Yeah. Yes. Yeah, I mean it might have to be an inductive recursive definition where you define the elements of the ordinals at the same time, if you see what I mean. But it's possible. I mean, it would make it even more complicated, of course. But. Yes, I guess one complication, let's see if I can dare to go back that far. It's also an interesting suggestion. One possible complication is that hidden inside here is a negative occurrence of the index set, right? This is for all I in n. So it really would have to be induction recursion where you're allowed to have these kind of half negative occurrences. It couldn't be a purely inductive definition in that case.
So while we're here, you talked about prop x at the beginning. I guess one place where you need prop x is to do this, the characterization of the less than equal relation. Yeah. Are there sort of other notable places where it comes up?
I think that's the big one, and obviously all over the place for the book ordinals as well.
Sure. Yeah. Any other questions?
So just a remark on the previous question, whether this map from Counternormal forms to Brouwer trees is a simulation. I don't think it is, because if you have a Brouwer tree and you know that it's relatively small, say below epsilon 0, you cannot find a Counternormal form, which would get mapped to that.
Right, it will be like computing limits again, I suppose.
Yes. And I mean, saying that this is a simulation would almost give you a partial inverse from the type of small Brouwer trees to CNFs.
Right. So yeah. So I guess you could compute limits, like Fredrik just said. You could include in, do the limit there, and then find the Cantor.
Yes.
Yeah.
Exactly. Yeah.
Yeah. I mean, that's basically the reason why this is not a simulation. It is because you use this partial inverse to go back and decide things here, and then you push it forward again. So yeah, simulation is quite a strong property. Yeah, I was hoping it would work here because everything is so nice and decidable, but yeah, there's still things we can't compute here, so that's a good point. I don't know, Nikolai, if you have any other comments, anything I missed or misrepresented.
No, this was all perfect.
So I don't know if Shang-Yi is, are you in the audience? Maybe not. The problem of just talking to your screen, you don't know who you are.
Okay, well, I guess we'll end the recording here. So let's thank the speaker once more.